Hello everybody, and welcome to this new paper explained. Today we're going to have a look at this paper from Facebook AI research from 2020 named Momentum Contrast for Unsupervised Visual Representation Learning. So this paper, although it's a bit old now, I find it still quite relevant since it provides an opportunity to talk about contrastive learning, and it's also quite elegant, in my opinion, how the technicalities that the authors provide for solving one of the main problems of contrastive learning, and it's also one of the approaches that is used also in state-of-the-arts, or acts as a base for novel state-of-the-arts that are coming out today. So today, more in detail, what I would like to do is to give a bit of a recap on contrastive learning for those who are not super familiar with it. And then we'll have a look on the previous approaches before the idea of momentum contrast was proposed. And this will help us build onto the momentum contrast idea, and we'll see in detail how this works. And then finally, we'll have a look at some of the key results that this paper proposes. And then, since I have an implementation of this paper on my GitHub, which is linked down below in the description box, we'll also have a brief look at the key components of the implementation, so that you can also go and experiment with it and play with it. Okay, so let's first start with contrastive learning. So suppose that we have a model and that we have a task that we like to solve with this model. So for example, suppose that we have a task that could be, for example, object detection or semantic segmentation or whatever task we want. So how do we train this model? So the first thing is that we can do is simply have a random set of weights, right? And then what we go and do is we have our predictions, we have our ground truth, and we go and minimize the loss, so that the model actually goes and learns how to solve this task at hand. Now, this is a completely valid approach. However, what people found out is that if we don't start from random weights, but we start from a pre-trained model, which has weights which do not actually solve the task at hand, so the model would not be able to perform any of the tasks that we are interested in, but these weights are, so to say, representative, or they are basically a very good starting point for then learning the task that we want. Then people observe that this actually leads to much better performance or quicker convergence, or has a lot of different advantages than starting from random weights. So contrastive learning, it's in the context of momentum contrast, it's used as a pre-training task. So we want to pre-train our model so that then when we start and train our model on the task that we really want to solve, then it performs better. So let's see how this works. So suppose that we have our model, right? And here I would actually go and modify a bit the structure, because we are actually not completely interested in our model, but we are interested in a subsection of our model. So we usually, so if this is our model, right, and this is the task that we want to solve, what we would have is that we have a backbone, and then these are the extracted features, and then we have a head. And the head can be, for example, a semantic segmentation head, an object detection head, and so on. And this is, of course, a very simplistic representation. Of course, with different models, we have different architectures, but just to have a bit of an idea. Now, in contrastive learning, we are only interested in the first part, and so we are not interested in training the head, but we are only interested in training the backbone, which gives a set of features, and then what we can do is then we can use the set of features, as we said before, to go and train the head itself. So let's just remove then the head, right? And let's just focus on this. And For our context, this will be our model. Okay. Now, suppose that we also have a training set. And here I would like to point out something, which is that the training set that we have here, so this our data, might actually be completely different from the training set that we will then use to solve our task. So a good example of a training set is just we go on the internet and we take a bunch of random images, right? And often we actually have no labels for this. So we only have the raw images, and we basically have no information about these images, or we might also have it, but in this case we, as the title of the paper says, is in an unsupervised setting, so we only have images. Okay, now since we don't have labels, we would like to still go and minimize something, right? So we would still like to go and minimize a loss that does something, right? And this loss should be such that the features that are then learned here out of the backbone are, as we said before, general and representative and can be a good starting point. Okay, so how do we actually do this? So as we said before, our dataset does not contain any ground truth, but it only contains raw set of images, right? So here we have height and width time channels, and these are all of our images. Now, how can we actually go and train our model if we don't have any labels? One simple thing that we can do is we can have augmentation of an image, and then we can teach our model to actually recognize that the image and the augmented image are the same, right? Or have the same features, vectors, but the augmented image is different from another image, right? So let's just make this a bit more clear. So suppose that we have the first image, x1, and suppose this is just a picture of the letter A. And then suppose that we have a second image, x2, the letter B. Now what we can do is we can actually go and augment. So we apply an augmentation to A, and just now for simplicity, suppose that we simply flip this. And now we have that x1 first, and x2 are simply images of height, time, width, time, channel dimension. And here I would just like to point out that the dimension of x1 doesn't have to be exactly the same as the original image. So one of the possible augmentations that we can do is, for example, simply go and take a crop or whatever other augmentation that we can think of. But now for simplicity, let's just simply say that we flip the image. Okay, so what do we do with this image, augmented image, and another image? So let's first start by giving some names exactly to these images. So usually in the literature, this augmented image is called a query. This is called a positive key, and the extra image, so which is different from the original x1, is called a negative key, right? Okay, so now that we have defined some terms, what we can go and do is feed these images to our model. So suppose that we have d of q, right? D of q is equal to f of x1 first, right? D of k plus is equal of f of x1, and d of k minus is equal of f of x2. Now what is d here? D is this feature vector here. So here in this case, all of these feature vectors have dimensionality of r by d by 1. So it's just a d by 1 feature vector, which is the output of our backbone. Now, what we can do here? So in contrastive learning, one simple way of applying contrastive learning is just making sure, or like just training the model so that the query that we have, right, or the feature vector of the query is very similar to the positive key and very different from the negative key. Okay, so since we have high dimensionality vectors, what does it actually mean to be very similar, very different? So let's just simplify ourselves, and let's suppose that our D in this case is equal to 2, so a two-dimensional vector. Now, the way that we measure dimensionality, or like similarity rather, is by using the cosine similarity. And now let's just have a very, very quick look on how this looks. So suppose that we have two vectors. Suppose that we have x1, right, and x2. Now the cosine similarity is simply the projectile of x2 into x1, and so this here is the cosine similarity between x1 and x2, and this is usually represented by the dot product. Now in this case, x1 by x2 is greater than 0, and we can see that we have, for example, this case where we'd have a value greater than 0, but then we can have a complete match. So we'd have that both x1 and x2, right, x1, x2, suppose that now they are completely matching, we'd have that x1 by x2 is equal to 1. And then for the similar vectors, what do we want? Suppose that we have this one, x1, we'd actually want something which is quite opposite to x2. So that the projection is here, and here we would have that the projection, or the dot product between x and x2 is less than 0. And in the case where our x2 it's perpendicular to x1, this exactly equal to 0. Anyways, long story short, cosine similarity allows us to perform a similarity measure between two vectors, also in high dimensional space, and it's just a single real value. So at the end we don't get a vector, but we simply get a real value, and we can interpret this value as, if it's greater than 0, means that the two vectors are similar. If it's exactly equal to 1, it means that they are exactly matching, and if exactly equal to -1, so the opposite case here, it means that they are completely opposite. So what can we do? We can actually go and apply this concept of cosine similarity in the loss function that we use to train our model. So I simply took a screenshot of the momentum contrast loss, and so that we can have it as a reference, and even for a simple case like the one that we're observing, the loss function is very similar. But let's just go and maybe simplify a bit this loss function just to understand the core idea. So our loss function, right, is similar, so it's the minus logarithm of the exponential of q times q plus here, over the sum e, right, so let's call this total number of keys k, and let's just call it q times ki. So here what we did was to simply ignore for a second the temperature parameter, and this temperature parameter, we'll see later that it's just a simple constant, so it's just a real number which is fixed also during the experiments. So, but it's not fundamental to understand the concept. But now let's focus on this loss function, and let's understand why, by minimizing this loss function, we can actually go and incentivize the network to have that the feature vectors of our queries and positive keys are very similar, so they have a high cosine similarity, and the feature vector of the query and the negative keys are very different, so again, by minimizing the cosine similarity. So here, if we look at this loss function, this reminds us quite a bit of another function, which is the sigmoid function. So suppose that we have the sigmoid function of the value xi belonging to, for example, a set of values x. So we'd have, for example, x1 and, for example, xn, right? So if we want to compute the sigmoid of this vector, what we would have is we apply the exponential to e to xi, and then we sum over all of the possible x's. So in this case, u of xj. Okay, so what does the sigmoid function do? So the sigmoid function, it's a sort of indicator function which allows us to project everything to a range of between 0 and 1, right? Because the exponential renders everything positive. And then we basically have that if the value xi is the greatest one, right, out of all of these n values, what we'll have is that also the sigmoid value of the value xi is also the greatest one, right? So this allows us to normalize between 0 and 1, and also to express sort of a continuous index which or like the rank of all of the possible n values. Okay, so let's see now how exactly this loss function works as a whole in the specific case, and let's see what it's trying to minimize. Now, if you go back to our example, what we see is that we have three vectors. We have dq, dk plus, and dk minus. Now here we drop the d, but they're basically the same vectors. So what we have is that we have q, k plus, and k minus. Now, what dot products are we computing here? We are computing q by k plus, right? Then we are computing in the numerator q by k plus plus q by k minus, right? Now, if the dot product between q by k plus is equal to 1, so suppose that we have a perfect match, here we will have 1, and suppose that here the dot product between q and k minus is 0, for example, in this case. What we'll have is that we'll have 1 over 1, right? And the logarithm of 1 is 0, right? So the loss is 0, so the model has learned perfectly how to minimize the dissimilarity between q and k minus, right? And to how to maximize the similarity between q and k plus. Okay, now let's look at a case where our model is not doing well, right? So let's look at the opposite case. Suppose that here we have a very small value. So suppose that here we are having 0.1, and suppose that here we're having 0.1 again, so same value, and suppose that here we are having 0.9. So what we'll have is that we have 0.1 over 1, so in this case, so it's 0.1, and we'll have the logarithm of 0.1, which is equal to minus 1. Minus by minus, this becomes plus, right? And so our loss is greater than 0, so our model is penalized, and we basically need to change the weights of our model so that the model performs better. Okay, so now that we have understood a bit better how contrastive learning works, let's have a look at how the baselines which momentum contrast presents look like and how they work. So the first one is called end-to-end, and the idea is that the encoder for the queries and the keys is updated end-to-end. Now let's see how this looks like and why is this important, or why is this a valid approach. So suppose that we have our data loader, right? So suppose that we have X and we iterate in our data loader. And so in our case, we have X. So now it's a batch. So it's B by height, by width, by channels, right? And suppose that in X, here we have B images. So X1 to XB. Okay. Now, what do? Similar to before, we go and randomly pick between 1 to B, just one sample. Just in this case, let's pick S1, which will be the base for our query. So here, what do? Here we have that XQ. So the query is just an augmented version of X1. And then what we have is other two different types of vectors. The first one will be xk plus, which will be x1. And then we'll have a set of other key vectors, which will be negative keys, right? And now let's just follow the indices of here. So let's just call this 2 because this is x2. Let's just go up to xb. So here is x of k minus. So k minus b of x b. So now, similar to before, what can we do? We have our model, right? What we can do is simply go and feed it the xq. That will be our query. So f xq. Then we'll have our k plus, which would be f of xk plus. And then we'll have f or k minus 2 of f k minus 2 up to k to b minus just f of x b k minus. And again, all of these vectors here have dimensionality similar to dimensionality of our backbone, which in our simple case is a d by 1 vector. Okay, now what do? We simply go and apply the loss function that we saw before. So we try to maximize the cosine similarity between the query and the positive key. So again, the query is just a different representation of our positive key, and we make sure that also the other representations of the negative keys are very different from each other, and so that our loss is basically minimized. Now, if you look at how the authors depict this, what we have is that here we have basically a gradient which goes and changes the encoder for Q and K. In our case, we are using just the same encoder for Q and K, but there are also methods which use two different encoders, but let's just keep things simple. And what the network is basically trained to, or what is actually leveraged, is that given a single batch, right, we have one positive example and b minus 1 negative examples that our network can leverage so that it can basically have, as we said, a positive examples and b minus 1 negative examples, so that it can learn to associate feature vectors in a way that we just discussed. Okay, so good enough, right? Not quite, because what people found out is that if you were able to actually increase this batch dimension quite a bit, then you would actually get better results, because your network is able to see more of counter examples or negative examples, and so the performance of the model would basically improve if the size of the batch increases. However, there is a catch here, which is that it's very difficult to fit a large batch of especially high resolution images, but also of low resolution images in a GPU. So the authors of the momentum contrast present some numbers where they show some of the baselines, but it's basically at maximum a couple of thousand samples where you can fit. However, if you increase the size of the batch, so this is just a preview of the results. So we can see that here, for example, the end-to-end is trained up to 1,000 samples in the batch size. We can see that the performance from 2256 to 1,000 for the end-to-end approach increases quite a bit. And just as a spoiler, we can see that if we are able to increase the so in this case it's not a batch size, but basically the number of negative keys quite a bit, then the performance is also increased quite a bit. So people thought of different methods on how to do this, and one very popular approach is this method called memory bank approach. Okay, so the memory bank approach. Let's have a look on how this works. So the idea is quite similar to the one that we saw before. So all of the math is very similar. The only thing that differs is how we actually go and select the negative keys that we have here. So in the end-to-end approach, it's quite simple because we go and select them from the batch that we have. But here we do a bit of better thing, which is that we have a data loader, right? So let's just go a bit slower. Here we get the queries, right? So we have XQ, right? And then we have the positive keys, we have the negative keys, and so on. And suppose that this is the first run of our data loader. And again here, let's just say that we are using a simple memory bank approach, and we simply use whatever we have in our batch. However, once we have finished the first iteration of our data loader, what we can go and do is put all of the features vectors for the keys that we had here. So all of the k minus, so in this case, we call that k2, k minus b, right? And we just put it into this memory bank. Okay. Now, suppose that we are now in iteration 2, we load our batch, and now we can select a query from our batch, right? However, the cool thing is now what we can go and do as negative queries is to select both what we have in our batch, but also take the keys which are in the memory bank, right? And use them for our contrastive learning. So here in this case, what we have is that different from the end-to-end approach, from the simple approach, we have that our key is not anymore the batch, but it's expanded. In the second iteration, for example, if you use everything that we have in our batch, we just have b-1 keys, right? And then we will have another batch of keys. So we have almost doubled whatever we had in our batch. Then again, here we are not limited because we can go and do this again, right? So we can go and save again in this memory bank the second iteration, then the third, and the fourth. And what we can see here is that memory bank grows quite a bit, right? And with the more it grows, the more counter examples we have for our model to basically learn to output different vectors for the negative samples. Now, this is an idea which, as we saw before in this teaser of the results, works quite well. And maybe let's just clean this up a little bit. But what we can basically see is that the performance here on the ImageNet linear classification protocol experiment, what we can see is that with the increase of the memory bank, and again here we can see that the memory bank can expand as much as we want, or as much as our resources allow, it's basically improving the results from, in this case, from 50 to 58. However, there is one thing which is not ideal in this approach, let's just say. Let's see if we can spot it. So for each iteration that we put data in the memory bank, and suppose that this is our first run, right? This is the second run, this is our nth run. What we'll have is that when we are in the nth run of our data loader, right, we will have that the first run of these features was actually encoded with a feature encoder, right? So suppose that we are having x2 of k minus, which is n iterations older. So the parameters that we used of the model that we used to encode the negative keys are actually very old and might be very, very different from what we are using now to encode the queries. And why is this a problem? This is a problem because if the features are very, very different from what the model is generating in the current batch iteration, then we could have that the model doesn't really learn an appropriate representation, right? So it doesn't really learn to predict features vectors which are, as we saw, different from the query. And we can even have cases where the learning doesn't happen, or it's very or is very hindered by the fact that the features are so different that the model can immediately spot what is from the current batch and what is from very old batch, and so it so the learning is a bit hindered because the task is much simplified, so to say. And this all because what we have here is that we simply store negative keys which come from models weights which might be very old. And this is exactly at the core of what the momentum contrast paper proposes, and it actually proposes a simple and elegant way to actually not completely fix, but at least minimize the impact that these old features that we get from using a sort of memory bank approach have. So by this evolution of the features, it's cleverly solved. And now we can simply go and see what is at the core of the paper. So now let's have a look on the key concept of the momentum contrast method itself. And let's see how it differs from the end-to-end approach and how it differs from the memory bank approach. So the first main difference from the two approaches that we saw is that the momentum encoder paper uses two different encoders to encode the features. So similar to what we saw before, right? So let's see the first example that we had. So in the first example, what we did was we took our model, right? Then we generated the feature vectors for queries, positive key and negative key. And then similar to the end-to-end approach, we did the same. And for the memory bank approach. At each iteration, we encoded the features, right? And the key features were sampled from the memory bank. Now here, it's a bit different because we have our model, right? And then at the beginning, what we do is that we separate the, or we copy basically the model, one for the queries and one for the keys. Okay. Now again, in the paper, they also use basically the same architecture for all of the three models. Basically share the same architecture and the same set of initial weights, right? But the key difference is that the model which encodes the queries is updated via gradient descent, right? So it computes a loss function, right? And then the weights are updated so to minimize the loss function that we saw before. And the key idea here is that the feature encoder for the keys is actually updated utilizing momentum, right? And I think this is probably the key contribution of the paper, and it goes really at the core of the main problem of the memory bank approach. So let's have a look at how this looks like. So a momentum update has basically a parameter m, right? And in the experiments, the authors set m to a very, very high value, so 0.999. And what this looks like is that the parameters of the encoder for the keys, it's updated by taking, in this case, 0.999 of the parameters of itself, right, plus 0.001 of the parameters of the query encoder. And so what does this mean is that the parameters of the key encoder change extremely slowly, also when compared to the parameters of the query encoder. Now, why is this desired? This is desired to exactly tackle the problem of feature discrepancy that we had in the previous approach, so in the memory bank approach, where we reach a certain number of steps, and basically very old features are, very old features are so different from the current features where the model has struggled to effectively learn from them. But here, although we can basically iterate through many steps, the features, even at very far away iterations, will be of course different from the features that we are generating the current steps. But since the update is very, very slow, this discrepancy will be much less effective or much less present than if we basically were using features updated directly from the gradient descent, as in the case of the memory bank. And so this is the first key contribution of the paper, which is you go and slowly change the features instead of having a fast-moving feature encoder parameter. Okay, now the second contribution is that they propose to, second contribution, which goes hand in hand to this first contribution, is that instead of having a generic memory bank, they specify that their memory bank is a queue, right? And the queue has a hyperparameter, let's call this L, and L is the number of batches which the queue can contain. Now, at each iteration, what we do is that we take all of the key features, right? So K plus, k minus 2, and then kb minus of number 1, and then of iteration number 1, and then for iteration number 2 we go and put again the same thing. Then at a certain point what we'll have is that we would have reached, right, L batches, right? So this would be iteration number L. And then once we've reached this, what we can do is simply go and take out the first batch and insert the current batch. And this is also a nice thing to do, or like the correct thing to do, because although the weights of the key encoder are slowly moving, these after L batches would still be the ones which are most different from the current ones. And so this again helps with this feature consistency that helps the model learning. And so these are the two main contributions of the paper: slowly moving weights for the key encoder, and a query system which can be expanded as much as we want, and that it's implemented so that old features are moved first when inserting new features. Now, let's have a look now at a pseudocode implementation of the momentum contrast, and let's go a bit through the code and how the authors implemented. So first thing first, what we can see is that what we saw before, so that the parameters of the key encoder and the curious encoders are basically initialized the same. And then what we do is that we get a batch, right? And then here it's a bit different from how we explained the basic experiment, but also very similar, which is that we take the first or we take the batch and we apply two augmentations. So we have the query and key augmentations. And so this basically will have B images, right, which will have one set of images, and then we'll have another one augmented, right? So for example, here it will be here. Let's just do our previous augmentation, right? So just some flipping. And now, very important, we see that we go and encode. So we have that the queries are encoded utilizing the query encoder, and then the keys are encoded utilizing the copy of the model used for the keys. And then, as I was saying, what we see here is that we actually go and detach the gradient for the keys. Why is this the case? This is the case because, like we saw before, the model will be actually updated utilizing a momentum encoder, and so nothing that comes from the encoding of the keys will need a gradient update. And so utilizing the PyTorch function detach, we simply remove the gradients from the calculation. Okay, so now I would just like to highlight two experiments which in my opinions are very important, which is basically this table here. And here the setting is the following. So the authors go and train with momentum contrast, and then an object detector, in this case faster RCNN, and then the object detection weights are fine-tuned on PASCAL VOC. So basically the idea that we're saying at the beginning, where we don't start from scratch from our weights, but we start from already a pre-trained set of weights. And in this case, the task is object detection. And here I think two things are important. First of all, if we look at the performance of this model with randomly initialized weights versus, for example, the first experiment with momentum contrast, we can see that we have a huge difference in average precision results, which clearly highlights that pre-training is not just a gimmick, but it's really something which is super powerful and then can really bump up the results quite a bit. But also the second result, in my opinion, is super important, is that the authors go and perform a pre-training in a supervised manner. So here we have that they use ImageNet 1 million, and ImageNet 1 million has also labels, and so they basically pre-train the model in a pretext task, which also includes labels. And what we can see here is that the difference between the supervised and unsupervised results is actually very minimal. And this is a very important thing to have, because this requires quite a bit of effort to gather. So all of the labels for 1 million images, depending on task, is quite a challenging thing to have. But this is completely done in an unsupervised manner. So here the only thing that we need to do is to gather the images, and the authors show that the gap between supervised and unsupervised pre-training is pretty much closed, at least in this experiment setting, which is very powerful if you consider how much we can actually go and scale unsupervised methods. Okay, so with this, I think we went through the most important concepts of the paper, and here and next I would just like to show some of the key components of my implementation of this, so that we can wrap up and conclude this paper explained. So I went and implemented the momentum contrast paper. You can find it linked down below, and you can also have a look. The implementation is not really aiming at achieving high performance or implementing all of the experiments, but I feel it's a very simple implementation which can help understand quite a bit the concepts behind. So let's have a look at the paper, or at the implementation itself, or at least at the key concepts. So here I have my training loop. So here we iterate over different epochs, and here we train a single epoch. And before training a single epoch, what we go and do is what we saw before, which is we initialize the encoders. So we take our model, and then we basically say that the query encoder is directly our model. Then we make a copy of the key encoder, and then we set this into eval mode, since we will not be updating it via gradient descent. So then we go through the data loader loop, and what we see here is that we get a batch, right? And then we augment this batch, we encode it. Again, here we see this, here we detach, because none of the features which will be used or which are extracted from the encoding the keys are actually updated via gradient descent, but they're be updated using momentum. And here, similar to before, we basically compute the same matrix multiplications, and we compute the loss function. We we basically compute the gradients, then we optimize, then here we update the key encoder. And here what basically is going on is that we simply go and update the parameters, taking m times the value of the current parameters plus 1 minus m, the parameters of the query encoder. And this is basically iterated, and after we train long enough, then we'll have a set of features which are quite representative. So as a final thing, I want to show the result of a trained model. So here I trained a model on my laptop for 10 epochs. So it's, as I said before, not really trying to aim at the performance of the original paper, but just to give an idea. And the way that I evaluated the model is just, as we saw to the theory, to see if the model is associating similar vectors with queries and positive keys, and different vectors with queries and negative keys. So what do we do here? So we have of our validation loader, right? And then from our batch, which in our case, it's a batch of size 2 by 3 by 512 by 512, so 2 images. I take the first image and I call it A, and then I take the second image and I call it B. And here I went and plotted the first image and then the second image. And what we do is that then we go and generate 2 augmentation, one for Q, so one for query, one for positive key. So we saw this was A, and then we can see that positive key is this one, and sorry, the query is this one, then the positive key is this one. So we see in this case we had random crop plus random color shift. We do the same for B, so this was our image B, and then we see that we also apply an augmentation to the negative key here. And then what we do is we go and using our model, so in this case we do not distinguish between FQ and FK, but here is basically our FQ model that we were having before, where I loaded a checkpoint and we basically embed the feature embedding for Q, for K positive and K negative. Now what we can go and do is simply compute the cosine similarity or dot product between the two, and we can see that the cosine similarity for Q and K positive is 0.45, and for Q and K negative is minus 38. So here I went and ran another batch of images just to see another example, and here you can see this is the first image, this is the second image, and we can see that the query is this one, then the positive key is this one, then the negative key is the following. And what we can see is that the cosine similarity between query and positive key is 0.97, whereas for query and negative key is 0.21. So it seems that the model, although it was trained for very few epochs, it's actually working. And yeah, this shows that the model is learning exactly what we trained it for. Okay, so with this, I conclude this paper explained. It took me a bit longer than expected, but I'm happy that we went through this very nice concepts that the authors presented and the underlying theory behind it. And I'm very much looking forward to the next one. Bye-bye.